Hello, these will be the notes for section 7.4, which is congruence theorems based on the exterior angle theorem. So we'll just remember that we already know a few rules about when triangles are congruent. We have a side angle side rule, we have a side 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 rule, and we have angle side angle. Those are all postulates. We'll actually have a few theorems in this section, things we can prove, that tell us other situations when we know triangles will be congruent. But we're going to start with something called a lemma. So in higher mathematics, a lemma is a minor fact that's proved in advance of proving a more important theorem. So we know we're going to need this fact very soon, so we just kind of prove it by itself to get it out of the way. So here's the lemma we're going to use here. So suppose we have triangle ABC with D between A and B. So let's draw a picture. So here is my triangle ABC, and D is somewhere between A and B. So what this says is, in this situation, angle B and angle ADC are not congruent. And let's think about this. We just learned the exterior angle theorem. So let's focus on triangle BDC. Focusing on that pink triangle, we can see that angle ADC is an exterior angle. Angle B is a remote interior angle. So we know that this exterior angle is bigger than this remote interior angle, which means they're not congruent. All we really need here is that they're not congruent, but we actually know which is bigger. So what this is saying is that the kind of diagram I'm about to draw is impossible. If I have a triangle and then I kind of break it up like that, and I claim, for example, that those two angles are congruent, that's impossible. The orientation of these is a little bit different, but it's the same arrangement. We can't have congruent angles like that. So just keep that in mind. We're going to need it in this next thing. So as I mentioned, we're going to add to the list of correspondences. So we know side angle side means two sides and the included angle are congruent to each other. Side 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 means three sides are congruent. Angle side angle means two angles and the included side are congruent. What about side angle angle or angle angle side? Remember, the order is important. This is not angle side angle. This is saying we have two angles that are congruent and a side that's congruent, but it's not the side that's included between those angles. So let's draw a diagram. Maybe we have a triangle like so. Maybe we have another triangle like so. A side angle angle correspondence would look like this. Side angle angle. Not the side included between those angles, but a side, then an angle, then an angle. And the same pattern over here. This is what we mean by a side angle angle correspondence. This is not the same as angle side angle, but your intuition might be that these triangles are congruent, and we're about to prove that. So this is called side angle angle or angle angle side, just the same thing in a different order. Every side angle angle correspondence is a congruence. So let's draw a diagram here. I'm going to do this somewhat informally, not as a two-column proof, but I'll talk through the key steps. So let's suppose we have a triangle like so, and then another triangle like so. And I'll try to draw them so that they look roughly congruent, but I'm not literally using copy-paste. So maybe here's ABC, here's DEF. Our givens is that angle A is congruent to angle D. Angle B is congruent to angle E. And that BC equals EF. What we'll prove here is that the triangles are congruent. So I'm going to do this as a proof by contradiction. Let's suppose they're not congruent. So if these triangles are not congruent, something about them would have to be different. And let's just notice, I'm going to do something temporarily here. If AB were congruent, if segment AB were congruent to segment DE, we'd have angle side angle, which means the triangles would be congruent. So this couldn't happen if the triangles aren't congruent. So we're assuming the triangles aren't congruent, which means AB and DE are not the same length. So if they're not the same length, one of them is longer than the other, and we'll just assume one of them is longer. Mathematicians will often say without loss of generality. One of them is longer, we'll just suppose it's, say, the one on the left. If it were the one on the right, it would be the same steps, the same argument, but we'll just assume something. So without loss of generality, WLOG is an abbreviation for without loss of generality. So I'm being specific, but it's really not that specific. Let's assume that AB is bigger than DE. So now, let's let X be on segment AB so that BX is equal to ED. Right, so here's what I'm going to do. Let me copy this. So I'm assuming there's a point X, maybe like so that this distance from B to X is the same as the distance from E to D up here. And now let's draw in segment CX. So what we'll notice we now have, by angle side angle congruence, if we look at triangle DEF and we look at triangle XBC, oops, sorry, I want to mark this with a double stroke. Right, so let's just backtrack. I chose X so that the distance between B and X would be exactly the same as the distance between E and D. And I can do that by the ruler postulate. So we'll notice by side angle side, triangle DEF is congruent to triangle XBC. So then by CPCTC, that means that angle BXC, the top angle for this triangle, is congruent to the top angle in this triangle, which would be triangle EDF. Sorry, angle EDF. So angle EDF is this one. We're saying angle angle BX. Let me highlight this so it's really clear. That's the top angle in triangle DEF. Here's the top angle in triangle XBC. Those are congruent. But we already know that angle D is also congruent to angle A. So let's look at this diagram. We now have that angle XBC is congruent to angle A. And in our lemma, we said this kind of arrangement was impossible. It's violating the exterior angle theorem. Those can't be congruent angles. So this is a contradiction. right? So I did a proof by contradiction, aka an indirect proof. In my indirect proof, I temporarily suppose something. I temporarily suppose the triangles are not congruent. I found that that's a contradiction. So the triangles are congruent. So you don't need to remember the details of this proof, but you definitely want to know this theorem. We have added to our list of how to know triangles are congruent, and that's very powerful. So we used to have side, angle, angle, and side, side, side. Now we've got a new one called either angle, angle, side, or side, angle, angle. Two angles and a side is good enough, even if the side is not between the angles. We're going to add another one. So let's remember there's no angle, side, side congruence rule. But there's a very special case that's kind of like angle, side, side under very limited circumstances, if the angles we're talking about are right angles. So this is called the hypotenuse leg theorem, or HL. So it says, given a correspondence between two right triangles, if the hypotenuse and one leg of one triangle is congruent to the corresponding parts of the second triangle, then the correspondence is a congruence. Let's make this a little more concrete. So let's suppose we have a triangle ABC, like so. And let's suppose here is A, and here is B, and here is C. And then let's suppose we have another triangle like so. That is D, E, F. So I have two triangles, and we're assuming, first of all, that they're right triangles. So the measure of angle A and the measure of angle D are both 90. We're assuming AB equals DE. And we're assuming BC equals EF. So this is our setup. I have two right triangles. Their hypotenuses are congruent. Hypotenuse is the side opposite the right angle. And a pair of legs are congruent. By even using the word hypotenuse, it means I have a right triangle. So when I say the hypotenuse and leg are congruent, just to use the word hypotenuse means that I have a right angle. So I really do have three pieces of information. These sides are congruent, these sides are congruent, and by using the word hypotenuse, I know I have right angles in each triangle, so those are congruent. So under these circumstances, right, the pattern here is angle, side, side. Angle, side, side is usually no good to know triangles are congruent. But in this special circumstance, we will be able to prove that these triangles are congruent. And here's the trick. So I'll just walk you through the basic idea here. We're going to choose a point G so that D is between F and G, and DG equals AC. So what I'm going to do is I'm going to extend this line. We know this line goes on forever. I'm going to measure the distance from A to C. And then I'm going to measure the same distance over here. And wherever that lands me, I'll call that G. So this distance from A to C is the same as this distance from D to G. I can do that by the ruler postulate. However far I want to go, I'm allowed to go that far. And I'm going to draw in segment EG. We have a linear pair here, and this is 90 degrees, so we have 90 degrees over here. So we can observe by side angle side, triangle CAB is congruent to triangle GDE. Two sides in the included angle match two sides in the included angle. Okay, so what does that tell us? Well, then we can use CPCTC. So sorry, give me a moment. I did not review the details of this before I started going through this, so I'm just going to be a little bit slower in finishing this proof. Okay, so now we'll use CPCTC. We know a couple of things. So we're just focusing on these two triangles right now. The triangles that I'm highlighting in yellow are definitely congruent. So by CPCTC, we know, for example, that angle G is congruent to angle C is congruent to angle G. And let's just hide this so that angle G is obvious what we mean. Right, so those are congruent by CPCTC. And also, just focusing on those yellow triangles, segment BC is congruent to segment EG. So I can mark this with the double stroke. Well, now let's notice that this big triangle here, triangle EFG, is isosceles, which means the base angles are congruent. So by the isosceles triangle theorem on triangle FEG, we know that angle F is congruent to angle G, but we already knew that angle G was congruent to angle C. So these angles are congruent, and now these angles are congruent. So now, let's look at what we have marked for these triangles on the left. So I'm going to change my highlighting. This triangle here, now highlighted in orange. This triangle here, now highlighted in orange. We'll notice that angle, angle, side, purple dot, right angle, single stroke, matches angle, angle, side. And we just showed that angle, angle, side is a legit rule. So by angle, angle, side, also known as side, angle, angle, triangle ABC is congruent to triangle DEF. And those were our original two triangles. So that's what we wanted to prove. So this is our fifth congruence rule. So the old ones were side, angle, side, angle, side, angle, side, side, side. Our new ones are side, angle, angle, aka angle, angle, side, and hypotenuse leg. Always call this hypotenuse leg. Yes, it's kind of a version of angle, side, side, but I don't want you to think that angle, side, side has any generality. We call this rule HL. It feels like it only has two letters, two pieces of information. All the others have three. But just by calling something a hypotenuse, we know we have right triangles. So that third piece of information is implied. All right, there we go. So you have now expanded your list by approximately 67%, and this will make things easier moving forward.